So I'd like to welcome everyone today. Obviously, we've got lots of attendees, some of our board members, some of our staff, some of our corporate partners, some of our community, some of our families. So lots of people, and we're very lucky today to have David Ziegler, who's a paediatric oncologist and senior staff specialist at Sydney Children's Hospital. He currently is leader of the Brain Tumour Group at CCI, where he is also a researcher. So I think you're a doctor at the hospital and assistant professor at the institute. We're also lucky enough at the Kids Cancer Project to have David as the head of the chair of our research advisory committee, which is an international panel. So we'll ask David a question on that a little bit later. He's also the chair of the clinical trials at Zero Childhood Cancer program, which is a program that Kids Cancer Project are really proud of. We started funding that in 2014 before it started the clinical trial process. In 2021, less than those with a survival rate of less than 30% have access to that program. And then by 2023, with some investment from the Minderoo Foundation, the federal government, we will see all children in Australia have access to the Zero Childhood Cancer program. And David is as I said, the chair of that clinical trials program. We are very lucky also to have David as one of our paediatric oncologists / researchers in the Kids Cancer Project, and he's got a couple of projects with us. So we're very proud of the work he does for us and how he helps us at the Kids Cancer Project. So without further ado, David, I'll pass over to you to take the reins, and then we'll come back and obviously ask you a couple of questions.
Yeah, thank you, Owen, and thanks both for the very kind introduction and for giving me the opportunity to speak today and share some of I think there's some quite exciting stuff that's happening behind the scenes. So I'll let you guys in behind the scenes and share some of that with you. Let me just share my screen. I'll put that in presentation mode, so I hope you can see that. Please let me know if there's any issues, but I wanted to really start this story going right back to when I started in paediatrics and actually started in paediatric oncology as a resident as my first term. And this was back in the day where I think that was actually my phone that I had, where you could actually use it. People used it for making phone calls in those days. And actually Google was something that most people hadn't heard of, was just being tested out. And when I started, as I said, on my first term in paediatrics in oncology, I was a bit worried going onto the ward about what it would be like. I thought it would probably be something like this, very sad, very depressing, and very hard to take. But what I was surprised was that the paediatric oncology ward was actually more like this. There was happy kids, there was clowns, there was singing, there was music, and what I realized then, and that's really for a couple of reasons. One is that kids really are an inspiration. As long as they're feeling good, they just want to play and get on with things. And I think that's from that moment even till today, that's what continues really to inspire me. But also it's the fact that most kids actually do well. And I think the example of that is pediatric leukemia, where if you go back, this is actually a very famous person who had, well, a sibling of a famous person who had leukemia when she was a child. This is George W. Bush's sister and George Bush Sr.'s daughter, who when she was 3 got leukemia, the most common form of leukemia that we see in children. And they were told, there's nothing we can do, take her home. This is an incurable disease. And to give you an example of the reflection of that, a haematologist a bit earlier made this statement saying there's nothing worse than to make a diagnosis of acute leukemia. The family is deluged with suggestions, and in the meantime, the patient goes steadily downhill. Much as one hates to admit it, there is practically nothing to offer in the acute or rapid case of leukemia. And this is a graph that I think really reflects those advances that we've made from a time when this disease was incurable, where actually was a famous doctor in Boston, started doing experiments on leukemia cells in the lab and found some drugs that were active and started treating some of the first children and started for the first time to see them going into remission and having responses. And since then, we've done more and more trials to the point where now more than 90% of children with ALL are cured. It's one of the greatest success stories of modern medicine. However, not all cancers are like that, and not all children's cancers are like that. And that's really where I've focused my research and where we continue to really need to invest our efforts. And I think the worst of all of these cancers, well, I think brain cancer as a whole is actually now the single disease that causes the most deaths in childhood. And so that's really where a lot of my efforts have been focused, and our lab at the Children's Cancer Institute is focused on finding new treatments for childhood brain cancer. And the worst of all these brain cancers that really reflects how nasty they are is one called Dipg. And this is how children often present, with a very short history of symptoms. They're usually about 5 to 7 years age on average, but it can be younger or older. They often have minor symptoms like their eyes not quite lining up correctly or their head tilting. It's a very short period of time, but essentially we do a brain scan and we see this tumour there and we know that this child is incurable. And just like for the 1960s, a child with leukemia, we still have that same outcome for children with a disease like Dipg. And in fact, if you take that statement, which sounded so archaic, and you take out the word leukemia and you put in the word Dipg, and you say there is nothing worse than to make a diagnosis of Dipg, the family is deluged with suggestions, and in the meantime, the patient goes steadily downhill. Much as one hates to admit it, there is practically nothing to offer in the acute or rapid case of Dipg. So a statement which was archaic is actually still holds true to this day and really reflects why we urgently need research. And in fact, this is another famous person. This is Neil Armstrong. And this is his daughter who was diagnosed with Dipg. And it's reflective, it's something to think about, that he was able to get to the moon, and now we're talking about going to Mars, but still in that time, we've really made no advances in our treatment. And when we started this program, actually part of the issue was that no one was studying this in the lab, and Dipg occurs in the most critical part of the brain where you can't cut it out because that would be fatal. And in fact, no one was even happy to do a biopsy of this region because it was so critical and they were worried about the potential damage to the brain. And so we actually thought, how can we actually start studying this disease? And the only way we could do it was to actually allow parents to have their child's tumour donated after they had passed away. So we set up this national tumour donation program. And what we wanted to do is we had all these fancy new machines where we could screen thousands of drugs, and we really just to see, can we find any drug that's active against this disease that will start making advances. We were starting to learn about the genetic changes in this tumour, but no one had yet been able to do this sort of drug testing. So when we came up with this idea, we were basically told it's impossible. You cannot grow a tumour after a child has passed away. Therefore, if you can't grow, if these tumour cells are not alive, then you won't be able to do this drug testing. We won't give you any money. Go away, forget about it. And it was actually, and I think this reflects, why charities and the Kids Cancer Project and parents are so critical, because it was parents of 2 kids, Benny and Amy, who actually said, like we thought at the time, maybe it's not impossible, but it just hasn't been done yet. And it was actually through their efforts that we started, that they helped to raise funds, they helped us get the ethics, they helped us convince the ethics committee that this was safe, that this was ethical, that this was a reasonable thing to do. And this was actually the first time this is a shot of the first time we were actually able to grow these tumour cells in the lab. This was the first time anyone in Australia had actually done this, and one of the first in the world. And through that And we've actually gone on since then and developed mouse models of this disease, so we can now really study new treatments, not just in the test tube, but also in a mini mouse hospital, if you like, where we treat mice who have almost the same symptoms and progress as the children. And so we were able to do this drug screen of about 4,000 drugs, including lots of anti-cancer drugs and lots of drugs that we thought might be really exciting and active. And this is Maria in my lab who really helped start this program off. And what we found, basically what this graph shows you, each sort of dot on this graph makes up, there's thousands of dots that make up this line. And basically what it's telling you is that most of these drugs were completely inactive. This was a really hard tumor to treat, and the drugs, even anti-cancer drugs, were really not active. But what we were really interested in was there was a few down this end of this curve, which were showing actually there are a handful that are actually really powerful. They seem to be doing something, including, for example, the fact that 3 of these really powerful drugs were actually anti-malarial drugs, which really took us by surprise, in which we invested a lot of time and effort in. And to cut a very long story short, we've basically now shown that we've got a new drug that's actually based on these anti-malarial drugs, a drug called CBL0137. And the Kids Cancer Project has helped us develop this further. And we've now actually reached the point where we've shown in all our models that this is a very active drug against DIPG. It actually targets, to a certain extent, the genetic changes in DIPG. And it's one of the few that actually works in our models to actually have it really strong activity in the lab. And this will be a drug that we're now actually taking into a clinical trial that will be opening through the Children's Oncology Group, which is the biggest sort of trials group in the world looking at new treatments for children with cancer. And this will actually be the first time that not only this sort of trial with the Children's Oncology Group of a new drug is actually opened in Australia, but it'll actually be the first time that it'll be actually led from Australia based on our research. So we're really excited about this, and we're working hard with that group to make this a reality, hopefully by the end of the year. The second example I want to give you that we've also been really interested in, and I'll tell you about the ties with the Kids Cancer Project as well, is drugs that target the polyamine pathway. And I won't bore you with the details, but basically polyamines are really critical in cancer cells. And actually decades ago, a new well, now an old drug was developed that targets this polyamine pathway, an old drug called DFMO. And it was actually, we were in another childhood cancer, neuroblastoma, we've done a lot of work on it and actually had a clinical trial that the Kids Cancer Project helped support that showed that, and this is a child who had a very aggressive neuroblastoma, and he went on this DFMO therapy, and his disease, which was in his bones, as you can see, almost completely melted away. And basically, we knew that there's a small number of brain cancers that have the same driver as neuroblastoma. And if this drug works in that disease, we should try it in brain cancer. And what we actually found is that DIPG, irrespective of whether they have a similar driver to neuroblastoma, are actually really dependent on these polyamines and actually very sensitive to this drug DFMO. And here we can see, this is our mouse model showing that actually it works. It improved the survival of these mice, but it didn't cure them. So it worked a little bit, but not a lot. So it gave us a clue that we could do something, but it wasn't enough to say we should actually start treating children with DIPG. And this is basically a very simplified version of what we call the polyamine pathway. And this is showing you how this drug works. So basically this drug DFMO switches off this enzyme called ODC1. And basically it stops polyamines being produced. It switches off the cell's factory and stops the cell from manufacturing these important compounds called polyamines. But the cell we discovered has a very simple way of bypassing this drug. And that if we're stopping the fact, we're turning off the factory, it just pumps in these polyamines from outside the cell, and it can actually become resistant. And that's why we saw the drug working, but not working that well. And so we basically then took this new drug called AMXT1501, which blocks this resistance. It stops the cell from pumping in these polyamines. And so now we have two drugs working together, one stopping the factory and one stopping the cells being imported. And suddenly, I won't bore you with the details, but we just published this earlier this year in Nature Communications, actually showing that this is a really, really effective treatment in our models. And in fact, we think it's the most effective treatment that any drug that's ever been tested in any DIPG models. And so we're really excited about this. And again, working with our international partners, and a second trial of this drug, we're looking at opening again within the next year, which is really incredibly exciting. And then the third story I just wanted to briefly tell you about, which is another way of looking at not just DIPG, but any aggressive brain cancer. In fact, any aggressive cancer in children is, as Owen mentioned, the Zero Childhood Cancer Program. And again, this is just a list of all the names on the paper that we just published also earlier this year, or at the end of last year, which really, again, has gained international attention because it's really the most in-depth tumour profiling program in the world, where we take any child's cancer and in real time do an extremely in-depth analysis of this in terms of the genes, the switched on, in terms of looking for new targets, in terms of trying to find an individual treatment for each child, and to see if we can come up with any new treatment that might be particularly active in that child's cancer. And in about 70% of cases, we can find a drug target, and we can actually find a new potential treatment that child would consider. And an example of this, and I think this is a really good example of a really exciting, really important genetic change that we discover in a very small number of cancers, but when we find it, it can really be a game changer. And this is what's called a TRAC fusion. And this is basically where two different genes, which normally were completely separately, are fused, joined together, and basically switched on to make this protein called TRAC, which really is an important driver in these cancers. And what's really important about this is we have new drugs which actually work specifically against this gene and just switch it off completely. And we know that it can really be effective in many different cancers that have this protein. And as an example of that is a child who had a brain tumour which was extremely aggressive. She had chemotherapy, she had radiation therapy, and she had really failed all of those treatments and was dying. And we did this genetic analysis and we found she had this TRAC fusion. But at that time, we didn't know if these drugs would work in a brain tumour. This had never been tested. And so she was dying. She was being sent home, and we made this discovery. We managed to rapidly get this drug imported. It wasn't available at the pharmacy. We had to work with the drug company to get it sent in overseas. And she started taking, it was just an oral syrup, so she could take just one dose every day. And slowly she started to wake up, and slowly she started to become more alive and to start talking. And over a few weeks, she started walking. And within a couple of months, she was dancing. And we did a scan after 2 months, and we saw that these white areas here in her brain, which were all the disease spreading everywhere, were literally just starting to melt away. And after 5 months of treatment, they'd essentially completely gone. And it's really showing, I think, the power of this precision medicine when we can find the right patient and match them to the right drug. In some cases, we can see really exciting and dramatic responses. So it feels like there's been an incredible amount of work that's been done, and it feels like, in some ways we are climbing Mount Everest. We are looking at the hardest cancers to treat, cancers like DIPG, which are incurable, and other brain cancers. And we are now actually reaching the point where we're making some exciting discoveries and starting to see some effects in children. And we've reached at least base camp, and we're planning to continue climbing as high as we can, and really to reach the summit. And what we want to do with brain cancer is what's happened with leukemia over the last 50 years, but obviously we want to do it much faster as possible. And we can only do that with an incredible group of people, and this is just some of the people in my lab who've helped do all the work that you've seen, and also the people as part of the Zero Childhood Cancer Program. And we can only do that, as I said, with the support of, it's been parents who've driven this. It's charities like Kids Cancer Project who have really been incredible support for us to allow us to get to the place where we are at the moment, and to provide these proof of concepts, if you like, to show that, you know, perhaps the impossible might be possible, and perhaps we can find a cure for these very aggressive cancers. So I'll stop sharing, and I'm happy to take any questions.
Thanks, David. Thank you very much for an amazing insight into your research and where that's moved. Obviously, you mentioned there the importance of translational research. So if you were to explain translational research to the group, how would you do that?
Yeah, thanks. Yeah, that's a great question. And I think that's really, as I sort of indicated, the focus of particularly my group's work. And that's really about translating what we do in the lab and it's to the clinic, to make sure our real focus is on finding, being able to make a difference for children who urgently need treatment now. But it's not just translation one way, it's making sure we go backwards and forwards and actually working as closely as possible, bringing the science and the scientists and the doctors together so that the samples are going from the patient to the lab, from the lab, the results are getting back to the patient as quickly as possible. And I think, you know, that's what you can see with, you know, how we started with Dipg as an example. That was really our focus. We knew other people were working on the genetics of these tumours, and we made great advances there, but we still don't, you know, there's still a lot of that hasn't led to improvements in children's treatment. Our focus was, well, okay, it doesn't matter what the genetic changes are, let's just find a drug that works, that actually kills these cancer cells. And that's what's led to some of the discoveries that.
Thanks. So during your speech, you also mentioned then, you know, the obviously the Kids Cancer Project, but in philanthropy, the ability of that funding to allow you to attempt innovative and novel therapies and models, and you know, the Kids Cancer Project, our investments are quite often venture capital, because you go off and find something for a clinical trial, or you find further funding. Where does philanthropy play a different role to, say, the government funding or institutional funding, which a lot of our sponsors and supporters are involved in allowing us to do what we do? Yeah,
absolutely. So it's absolutely critical. It's really, you know, I think one of the key messages that I've learned is that, you know, we could only do this because of that philanthropic support, because, you know, really to get that government funding, we need to have basically already shown that it's possible, that we can do it. We have to have half the results there. But we can only get to that point because of this philanthropy that says, okay, we know no one else in the world has done it yet. We know this is high risk, but we need a treatment for these kids. You know, we're going to support you to do it. And so the two work together with, you know, with the money that's given to us through philanthropy. Once we have done those preliminary experiments and done that initial work, we can then go and get the government funding to say, okay, let's take it to the next level. So the two are really, they're really both very critical. And we couldn't have done, you know, that example that I gave you about leukemia starting in Boston, that was also driven by parents doing fundraising. And that still goes on to this very day. That's why we've reached the success we have with leukemia, and that's what we're trying to emulate with these cancers.
Yeah, so one of the, you also mentioned about DFMO, so obviously you mentioned the Kids Cancer Project. So it was 2014 to 2016 that we committed $300,000 towards the drugs and the clinical trial. You spoke about AMXT 1501, so we're just talking about collaborating with Neuroblastoma Australia to move that into clinical trial. You're looking at Dipg. It's a bit of a pipeline. It doesn't happen in 1 year, does it?
No.
In 3 years, you'll have an answer, because you're dealing with Dipg. So that is, if a kid gets a diagnosis, you average 9 to 12 months. That's if things go well.
Yeah.
So
yes. So
you've got your
you're
work
right.
cut out for yourself.
So it's that if that's the challenge, right? It's about doing it as quickly as possible to help kids today who need those treatments. If a child is diagnosed today with DIPG, as you said, we know they have that timeline, and that's why we want to do it as rapidly as possible. And that's why that's our focus. And yes, it's really critical we learn about what works. And as I said, that trial that you supported with DFMO, that's actually now gone for neuroblastoma into an international trial where we showed that yes, it can work. Yes, it has activity. And now there's a big randomized trial being done where basically for every child with neuroblastoma, half will get DFMO and half will get standard care. And that's rolled out internationally. So it's really, one small trial with 20 patients has now, gone global. And so that's incredibly exciting. And then, as I said, we learn from that. Well, and particularly a disease like DIPG, if we can find any treatment that works there, we're going to have to work out what other cancers it must work for as well. Because if we can treat the hardest cancer, and the most aggressive cancer, then this will be an important discovery and important to work out which other tumours it works for as well.
So we've got one question from one of our attendees. So I'll just have to read it off the screen. In addition to polyamine pathways, what do you think are some other main metabolic pathways in DIPG that can be targeted?
So yeah, look, I haven't had time to go into everything, but we have actually a big program where we're looking at multiple different pathways. So I'm sorry, I had to cut things out. I couldn't share everything, but for example, we're looking at immunotherapy, and we're actually about to open a trial of CAR T cells. So basically taking a child's own immune cells and making them attack their tumour. And so that's one thing we're looking at. We're looking at drugs that target what's called the cell cycle. We're looking at drugs that target the epigenome, so basically the master regulators of DIPG. And yeah, there's a number of other things that we're looking at. So I think we're trying to be as broad as possible, but obviously we need to be broad but also focused.
Yeah, obviously we're short of time, but if we can, that was from Philip. So if he's got any questions here, I'm sure you'll be happy to answer it. Just one last question from me, because there's not many coming from the floor. I know we're conscious of time and you're busy, but you spoke about your team and people, and when you spoke about your biobanking, you didn't mention that was a first in the world biobanking, David, that we're all very proud of you launching. That allows those novel therapies like anti-malaria, but future-proofing childhood cancer. So the biobanking and the importance of young researchers, that's one of our 6 priorities at the Kids Cancer Project. You have to have those younger people coming in, and the biobanking obviously lets you sustainability of tumours for the future. So what's your young team look like? How many of those young researchers do you have?
So we've got about 15 altogether in the team in the lab working on the brain tumours, and about several PhD students and about 4 young postdocs. And yeah, I think it's really hard. We talked about government funding for these early career people. It's getting smaller and smaller in terms of grants from the government. So it's incredibly important work and incredibly difficult work, and really hard for them. We don't to be always looking for money to get them to get to the next phase, which is really again goes back to why this philanthropic support is so critical to help these really incredibly smart, enthusiastic young researchers slogging away in the lab to make these discoveries. The DFMO that I talked about, we had no idea whether that would work, and it was this very young PhD student who took it on and really it's gained international attention now. And in terms of biobanking, I think if we don't have, as I said, DIPG is the great example of that. If when we started this project, no one had even heard of it in the lab because there weren't samples there for people to work on. Unless we have that, those samples in the bank, those samples in the lab, in the test tube, and the research can't be done. So they're both really critically important.
And then maybe just one other, I'll sneak one other in because we're just about to finish, but it's around your other role with the Kids Cancer Project in the Research Advisory Committee. So how important in lots of those funding, so you have some projects with us, but they're obviously, you have to drop out of those when we're funding, but you've also got projects through our government funding collaborations. And but how important is it? Because money there isn't a tree for us, and lots of our supporters are helping. How important is that RAC and the importance of peer review and those processes that lots of the funding goes through?
Yeah, so that's I think it's fantastic to be able to be part of that research advisory committee, because I think it's really critical that the people who are donating that money know that it's being spent in the best way, and it's really a thorough process that each application goes through to make sure this is the best research, this is the best investment, and this will give the best outcome for patients. But not only that, it's also what's fantastic about the Kids Cancer Project is that when we say this is a really good project, this is worthwhile, this is good research, the money's actually there. The problem with a lot of the government funding at the moment is that really great research reaches that threshold. The committee says this is good research, but there's simply not enough money to fund it. Whereas what's really exciting about our work for the Kids Cancer Project is when we make that call, when this group of experts says this is good, this should be funded, we know that the Kids Cancer Project is there to make sure it happens.
Yeah, and like you said, it's an international panel. We're very proud of the members that are on that. We won't go into who's on it now, but last year there was a commitment of over $3 million. Despite COVID, we didn't have any reduction in any of our funding, but those researchers led to almost $8.25 million worth of further funding. So our $50 million year to date has been more than doubled. So it's important. You yourself have got a recent grant from the New South Wales Cancer Institute from projects that are funded. So the review is important, but so is the translation that you just mentioned and the ability to get further funding and move this research to clinical trials.
Exactly. Yeah.
All right, everybody, on behalf of everybody online and the team at the Kids Cancer Project and our board members that are online and our staff that are all listening, David, thank you very much for sharing a half an hour with us. This is our second Behind the Science. So we look forward to sharing this with you, and you've individually amongst I think we've got 46 scientists that we've funded in the last 12 months, 32 research projects across 21 institutions in Australia. And it is the people that, like you, that we're so proud of. And like you said, your research is driven by the parents and the families that are in your clinic every day. And much of our commitment is on the same research and the same families that we deal with. And it's great to see sort of, lots of change. My 6 years here at the Kids Cancer Project, there's been some amazing trajectory in what we've been able to do. And as you mentioned, the research you're doing is novel and innovative, and we really look forward to seeing some futures in the coming years. So thank you for joining us, David.
Yeah, thank you very much. It's been great, and happy to chat anytime.
Thank you, everybody who's online for joining us. That's the end of our second Behind the Science, and I'm sure you're very appreciative of David sharing his time and giving us an update of where his project's at. So thank you all, and have a wonderful afternoon, and we'll see you later.